Okay, thanks, Amy. Yeah, so I'm here more or less to be at the service of the calibration team. So you can interrupt or ask questions or try to show me that you're bored in some way, although I can't see you. I thought perhaps the most useful thing to do would be, in talking about AXAF calibration, is what I would call the rest of the story. There's a ton of material that we've published in SPIE publications. There's this 742-page report, which you can find in the public CXC calibration website. So I'm going to talk about some of the presentations we've made for Marshall Space Flight Center, for the Science Working Group, for some of the technical communities that basically were presentations that explained how we were getting ready for calibration and things sort of behind the scenes. I'll be talking primarily just about the SAO mission support team efforts, so not the AXAF Science Center efforts, which from the early 90s were going on in parallel and in fact in coordination with us. And the whole calibration effort, of course, was a team effort with NASA, Marshall, and all the subcontractors. Now, an interesting feature is that we didn't have very much electronic communication in those days. All the presentations we made were actually on these acetate transparencies that we one by one put on and off of a projector to show. So I made the slides for this PowerPoint by taking cell phone snapshots of those. I'm not a great photographer. The quality is generally poor, so sorry about that. So mostly what I'll be talking about is the flight article calibration, the high resolution mirror assembly, and mostly what was done at the Marshall Space Flight Center X-ray Calibration Center. And I don't actually know if that's what you plan to use. In fact, as I told Amy, please don't tell me anything that's proprietary to your team, because besides not even remembering where I heard it, I'm not part of any team, and I don't think I would not like to restrict myself from what I say. Okay, so the rest of the story. One of the most important things about calibration, and this is a lesson that we learned from a private audience we had at Space Telescope Science Institute before the Hubble telescope was launched, is the requirement to calibrate an instrument and the ability to calibrate the instrument must be considered as part of the initial design and initial requirements of the instrument itself. Space Telescope apparently had lots of instruments that, or some instruments that came from sort of a historical culture of optical astronomy, where astronomers looked at pictures or looked at spectra and made conclusions from it, and actually made instruments that weren't easy or even possible to calibrate to the kind of precision needed in order to like ship the data out to the world and have them use it. I'm not going to talk about the content of software relevant to calibration, but software is a very important part of it. And there's at least three very broad categories. You need software to generate performance predictions in the calibration configurations. And I'll talk about performance predictions and error budgets and so on. Then you need a set of software to actually run the calibration operations. You're in a vacuum chamber, so you generally need to activate motors, move detectors around, move apertures around, adjust shutters maybe, and of course, to acquire the data and to tell you that you really did get the data that you wanted to measure. And then another disjoint somewhat set is software that you'll use to actually analyze the calibration data and prepare your final products. There's, of course, calibration of the calibration equipment. We won't discuss that, but it's important for considering in your error budgets, for example, things like detector efficiencies, precision of motor motions, sizes of pinholes that you're using, and the spectral purity and fluxes and intensities of the X-ray sources. And finally, a very huge calibration task is to do what you might call offline calibration. You measure surface reflectivities, thicknesses of coatings of things, transmissions of windows, and subsystems of detectors before you bring everything together for a flight article calibration. Forgive me if I'm being a bit pedantic here, but first thing you might ask is, why do we do calibration? And this whole slide is a condensation of a multi-page memo that we wrote explaining that basically to the project team and the contractors. The objectives of any investigation are to find out things about the nature of celestial objects, physics, processes, history, and evolution of the universe. To do that, you have to make certain measurements. And to understand the measurements you've made, you derive the calibration requirements to be sure that you're making the measurements you need to give you the information you need to satisfy the scientific objectives. Okay, then more precisely, what is calibration? Only a very few measurements stand alone that provide a definitive numerical conversion of things that you measure on orbit to a physical quantity. An example might be converting a broadband counting rate to a broadband flux. That's not possible to measure for all energies, for all off-axis angles, focal plane locations, et cetera, et cetera. So what you need to do is you need a model that continuously interpolates or predicts any of those quantities that you might want to measure. Then calibration helps you verify that the theoretical and empirical models of the mirror and the instruments and their combinations are valid. Calibration needs to overdetermine the numerical parameters that are used in those models and estimate the errors in those parameters, and therefore they estimate the errors in the models themselves. And in the development of AXAF, we actually had a case where we noted that something like an efficiency of 45 plus or minus 5%, which is a 10% measurement, is worse, that you'd rather build an instrument that had 38 plus or minus 0.4% knowledge, because that's a 1% calibration. Very hard for a contractor or even some managers to understand why you would want a smaller efficiency. In doing the calibration, you might find the models are inadequate or inaccurate. In that case, the calibration needs to provide you the data that you need to revise or refine the structure of the models. And finally, we want to relate, or we want to use the calibration to relate measurements that we're going to make to fundamental absolute standards: length, time, mass. So the bottom line of everything I might say today is that the model is the calibration, and that's the objectives. So I don't know if I need to show these pictures of AXAF mirror in the XRCF at Marshall Space Flight Center. I don't know if you plan to use it, although it strikes me that the 1.5 diameter mirror and the 4-meter focal length are ideal for placing the mirror right down here, much closer to the instruments that you use to measure properties of the mirror, because the entrance aperture here is a little less than 1.5 meters. So that may have been very deliberate consideration of your design. Anyway, we have the long tube here, another 520 meters to the left of this picture till you get to the X-ray sources, which approximated a point source at infinity for AXAF. Of course, with a much lower angular resolution, that'll be a much better approximation for the LEM. Okay, and then in the configuration to just calibrate the mirror, we have specialized detectors, and general purpose detectors, pinholes. We have the ability to move these detectors around, select different detectors, select different pinholes to make measurements. We also went from there to actually put the actual science instruments or science instrument prototypes into the chamber and calibrate them directly with the mirror. Now, early on in the development of AXAF, and in fact, in something like 1990, 1991, even before the program was canceled, it was recognized that there was actually no organization or person in charge of calibration, and that, of course, calibration is a crucial part of the whole mission. So a calibration task team was formed, and the scope of the work required a dedicated group of scientists, and I've just added this today, and others working together on a daily basis to define what calibration needed to be and how it would be done. So the what of the calibration task team is the organization that would do that, ultimately provide detailed specifications of X-ray generation and detection equipment to be used at the X-ray calibration facility. So the who is on the calibration task team is important. It was headed by the NASA project scientist, Martin Weisskopf. The other key participants were the AXAF chief engineer, Bill Taylor, and myself as SAO project scientist. And the working members included a lot of the Marshall Space Flight Center scientists and managers, and some of the scientists from SAO. I have to tell you an anecdote here. One of the, this presentation is to the AXAF Science Working Group, a very self-considered august body of people consisting of the IPI scientists plus 5 interdisciplinary scientists, plus Leon van Speebroek as the mirror scientist. So one of the curmudgeons on the group was looking at the SAO scientists and said, well, I don't know about that. What are Dr. Beatty's qualifications? I'm not sure I can approve him as being a member. So apparently he was the only person on the group that didn't recognize who Dr. TBD was. So the team was formed and started working. As I said, this is before the project was canceled and reconstituted, but the team did continue on. So under the phrase that Riccardo Giacconi invented, scientific systems engineering, the planned observations were the top level requirements, that is the planned on-orbit observations. And a requirements study was performed to flow down and allocate those requirements from the on-orbit measurements to what needed to be measured on the ground and integrating them all into a calibration plan. To do this, lots of models had to be developed. As we mentioned earlier, you need to interpolate the performance between the discrete measured points as continuous functions of energy, angle, etc. And just to repeat, the final models are the calibration. To get procedures, we needed to establish error budgets. We needed to iterate with the participants. So the key principles underlying the flow down of requirements is that the X-ray calibration facility would be used to calibrate the Herma, and then the Herma and the SI in those combinations at a number of discrete energies. Recognizing again that that calibration by itself is inadequate to fully characterize the devices. Further offline calibrations are necessary primarily prior to assembling in the XRCF. And these included, for example, synchrotron measurements of absolute reflectivities, derivation of optical constants from those synchrotron measurements, actual reflectivity calculations and measurements of samples that were coded along with the coding of the actual mirror, modeling empirically and theoretically, plus standalone science instrument measurements of subsystems of the instruments. And the mantra was that there would be two independent models for all the performance calculations to check and verify and be self-consistent. The two independent models didn't necessarily mean independent algorithms, but it meant independent implementations of the models to make sure that the implementation and predictions were valid and self-consistent and so on. So the major tasks of the calibration task team were to liaise with the science working group, with others that were defining on-orbit observations, developing detailed plans for implementing calibration and equipment, creating models, assembling models that were created to simulate performances, developing the detailed requirements for calibration, the specifications of equipment to be used in calibration, and in particular, the procedures for calibration. The procedures are especially important because, of course, that defines the exact timeline, and the time is money is never more appropriate than during this phase of the project where the prime contractors are waiting for the mirror and instruments to be delivered to them. And finally, it involved a lot of liaison with the instrument developers, the instrument principal investigator teams. So what is the product of the calibration task team? In principle, it was a single document that included the top-down derivation of all the calibration requirements, tying those requirements together via the devices of error budgets and relating them to the top-level requirements, putting the approaches and methodology all in one place, along with supporting analysis that in principle anybody could read to verify that, yes, this is the necessary and sufficient operations and equipment needed to be scientifically calibrated and to deliver what a $1 billion observatory should deliver to the community. Actually, in practice, multiple documents were created, and to be honest, not every scrap of what we defined to be developed here was really documented. So there's a notional timeline that was developed, and again, this was developed before the cancellation of the AXAF program. The key thing about this figure is to note the lead time between this calibration document being prepared and delivered and the actual start of calibration. it's a couple of years lead time, and of course you need that time to do the actual development of the instruments and facilities and write the procedures and so on. And I have to also note that with the cancellation and reconstitution of the AXAF mission, we actually started calibration in late 1996, so about a year delay relative to this time frame. So we needed to get inputs from the people who were doing the on-orbit observations to achieve certain science objectives. So we developed this sort of questionnaire of science investigation questions. We asked them, what instruments would you be using to do your investigation? For example, an investigation might be studying the cooling flow in the core of a cluster of galaxies. So maybe they would be using ACES for imaging or the calorimeter for detailed spectroscopy. And of course, the calorimeter and the Bragg crystal spectrometer disappeared from the reconstituted AXAF mission and are still awaiting flight today. So then that questionnaire went off to the interdisciplinary scientists, in particular to the instrument principal investigator teams. We asked them for offline and online calibrations. The key things are what parameters they needed to calibrate, what precision was required, and what assumptions are being made that derives that precision and which derives the kinds of operations that they'll do in the X-ray calibration facility. What assumptions are they making about what the facility will provide? Okay, so the role of the science working group is to provide an oversight for this activity. And the role of all the other AXAF participants are to support the calibration task team, providing inputs, attending at meetings, volunteering for doing homework tasks. And so we proposed a charter for the team to produce the scientific plans and specifications, work with all elements of the scientific program, and obtain necessary oversight from the science working group. By and large, I think this was successful and a key to planning and executing the calibration of AXAF at the XRCF. So not everything flowed from 1991 to 1996 exactly the way it was proposed in this very initial presentation to the project, but it was adapted and we derived what we actually needed to derive to do the job. Okay, so as we finished the calibration task team activities and we approached actually doing calibration at the X-ray calibration facility. So here's a presentation we made about a year and a half before the start of calibration to the project. So again, we started out with the emphasis on the fact that the model is the calibration, and that calibration was going to be measuring values and errors of the parameters of this performance model. The philosophy was that the calibration tests were designed in particular to probe elements of the models rather than trying to approximate on-orbit observations directly. So key elements of the model always involve things like the absorption edges of key elements. And we're viewing calibration as a physics experiment where we can vary the test configuration in ways which probe the performance model. So an example of varying conditions is nominally we would have the Herma axis aligned with the axis of the X-ray source to approximate a point source on axis. With the divergence of the beam and the finite source distance, it actually meant that not all of the mirror was being sampled. And in fact, it meant that the exact incident angle on the mirror was not the exact grazing angle. So for some of the measurements, we actually needed to tilt the mirrors to make a quadrant, say, of the mirror more nearly approximating the exact graze angle expected for that mirror. So wherever possible, we wanted to separate and isolate effects, testing the mirror separately from the science instruments, doing off-axis variations, which separated variations in the science instrument quantum efficiencies from variations in the Herma effective area. There's effects like obscuration due to the struts and the caps, variation in the angular distribution of photons from the Herma. That is, the Herma had 4 different shells, so it's actually producing 4 different cone angles of photons that are incident on the detecting elements of the science instruments. For the high resolution imager in particular, which was a microchannel plate that had pores slightly tilted to the optical axis, that principle was relevant. Okay, well, the most general property we can calibrate is the point response area, the actual area in absolute square centimeters for a given exact input energy at a off-axis angle of theta, an azimuthal angle of phi, at a position y and z in the focal plane, at a position x along the optical axis, if whether that's perfect focus or out of focus, and perhaps for some additional parameters that are just indexed as I. At the X-ray calibration facility, this I might have applied to the 4 different shells of the mirrors. It might have applied to the 16 separate shell times quadrant combinations, which we had shutters to allow us to select. On orbit, you might think of I as applying to 2 directions of polarization. I mean, it turns out that reflectivity is very slightly dependent on polarization above a few hundred volts. Possibly for LEM, you may be interested in polarization at your very lowest energies. I don't know. So various combinations, various integrals of this kernel have special names. There's the encircled energy area encircled within some radius that might be a linear radius in the focal plane and in principle are an angular radius. There's the total effective area that on axis at 0, 0 for a infinite distance in the focal plane or an angle of pi over 2 of the focal plane. Of course, this can't be measured directly, so needs to be inferred somehow. Then a useful quantity is the dimensionless point response function, the amount of area inside some encircled energy fraction as a fraction of the total area. So the Oops. Okay. So you'll notice that many of these slides refer to the verification engineering test article, which we just reused the slide in explanations for the actual AXAF flight mirror. So this was just the definition of what we measured for the verification test article. And the fundamental calibration concept was just to measure an absolute area of a mirror, and it's labeled with the verification mirror here, but of course is the same for the flight article Herma. The absolute area of this mirror in relation to an absolute area measured at the same location of the entrance parallel beam is just the ratio of the counting rates that are measured in the focal plane by a detector identical to this beam normalization detector. So just the ratio of these areas. And of course, since nothing is identical, and since none of these three numbers are measured with infinite precision, we have to do error budgets considerations of to what extent the detectors are identical and to what extent the counting rates are being accurately measured. So this leads to the topic of calibration performance prediction. So we want to predict what we're going to measure in any given calibration setup. We use this prediction to plan experiments. We want to ascertain that the correct measurements are being done to give us the information we need. The planning of the experiments then drives the requirements for the specifications for the equipment that we're using. It drives requirements for auxiliary measurements. For example, one important auxiliary measurement is that we scanned that beam normalization detector, which during an actual measurement is sitting to the side of the Herma, but we scanned it in front of the Herma, covering the full area of the front of the Herma for each of the different X-ray sources to verify to what extent the incident X-ray beam on the Herma was uniform, and to what extent the to what extent the flux at the side of the Herma where we were measuring the beam normalization detector was the same as the average flux incident to the Herma. We use performance predictions to ensure that our timeline of observations is giving us the sufficient statistics that we need, and that it's getting done in a predictable amount of time so that we can budget the available time. And of course, the time available for calibration was the hard constraint. And as Fred Rutalik emphasized over and over again, when the time runs out, we're taking the Herma out of the calibration chamber and shipping it to TRW, and we don't care if how many measurements you've made or what precision you've done. That's what has to happen. Of course, he didn't say it in quite so many words, but that was the precise meaning. And then we use the prediction, of course, to perform the actual calibration, adjusting models of the parameters until the prediction process agrees with the data. So, I mean, the next step beyond the calibration performance prediction is it's a prerequisite to construct an error tree. So we need to construct an error tree so that we can ascertain the sensitivity of a result that we measure to perturbations and uncertainties in all the inputs that go into that error. Just I've crudely handwritten here, for example, the encircled energy is some function of lots of parameters. The square root of the variance of that is just the root mean square of the variances of each individual measured quantity x sub I. And of course, these sigma here are not necessarily a sigma of a Gaussian distribution. They are rigorously the square root of the variance of whatever the distribution of errors might be. And of course, for systematic errors, that can be very hard to ascertain. So the error tree is used to construct an error budget of how well we expect to measure things, and then post facto to construct an error analysis to see how well we did measure things. So we wrote a 67-page error budget flow down, and just to show you, maybe to give you some flavor of the detail, is I'll walk through just a very few of these pages. So we want to know the Herma encircled energy to 1%, say. We divided that into contributions that are due to all the measuring equipment, the Herma X-ray detection system measurement equipments, the detectors and motors and so on that we used. And then there's the non-HD HXDS contributions. These are like the systematic errors due to the fact that we may not have the Herma in the right focus. There's a finite size and distance to the calibration source. We were worried about relative motion between the mirrors and the apertures just from, say, seismic effects, moving things around. We actually developed a detector, that is GRW, invented a detector that was the motion detection system that constantly measured the motion between the focal plane and the X-ray source as a continuous function of time, and proved that we never needed to use that, which was nice. Okay, so if we just follow down this HXDS contribution error, there's errors to the measurements that we're making with the beam normalization detectors, and the measurements errors of the focal plane detectors. If we're measuring an encircled energy, we've got a different size aperture in the focal plane for each of those. So that's why these two measurements are budgeted separately, whereas for the beam normalization detectors, it's the same aperture and it's just the ratio of the error that we're concerned with. So we'll follow this part of the tree down, the beam normalization detector errors. And there's a bunch of different terms. One of them is how well you've measured the flux during the maximum measurement, how well you've measured the flux during the time where you're trying to measure the encircled energy at the radius indexed by I. And we'll follow down how well you measure the absorbed line flux. Depends on lots of quantities. One of them is the detector gain shift. And I'm showing this slide because it's got the interesting feature. We have a 2% error here, whereas we had a 0.4% error in how well we wanted to measure the beam normalization detector flux. And that's because a gain shift is just really shifting the wings of the resolved line a little bit. So there's really a 4-to-1 multiplication in the sensitivity. And we see that multiplication factor again. The high voltage needs to change by only 0.06% because a change in the gain of the high voltage has a factor of 16 multiplication in the effect on the actual gain to meet the 1% gain. I'm just going to back up and follow. One of the other terms of the error budget was the correction for the actual size of the pinhole aperture, where we budget a very small error. And the size of the aperture can vary. In principle, it's a circular aperture of an exact radius, but it may be slightly elliptical. It's not an infinitely thin aperture. It's got to have some finite thickness in order to actually absorb the X-rays. So there's thickness effects. The apertures were made by laser blasting a little hole in them. That doesn't produce an exact cylindrical hole. It produces a conical hole with slopes. So the interesting thing you might see about this slide is that we didn't actually have numbers for any of these lower values of the error tree. And in fact, it's not clear that we rigorously established that the error was of that value. Okay, so now we're getting to the Herma Calibration Readiness Review. So this is a review in November 96, before we actually start the calibration process. And this is a presentation, again, made to the project by various organizations. And TRW was in charge of the test. They were the test conductor because it was their article, and their deliverable was the observatory. So they provided the test conductor and were in charge of the test. That the next level down, the SAO was the operator of the test, because we provided most of the equipment for the mirror testing in particular. Marshall Project scientist actually served as a supervisor of, if you will, of the test. So anyway, this is SAO making the presentation of what we were going to do for the test operations. So we defined subphases that we would conduct the tests in. We provided descriptions of all the test plans for all these specific measurements. So first we had to do a focus and alignment of the mirror. And then we measured encircled energy, effective area. We made those measurements by means of doing one-dimensional and two-dimensional scans with various pinhole sizes. Another thing we did was make actual full images of the mirror. We did that with the so-called high-speed imager. It was a microchannel plate similar to the high-resolution camera that actually was a flight instrument, but it was made so that it had a much faster response time, much higher count rate throughput. And we did ring focus tests, which helped us diagnose the ground gravity effects, and I'll talk about that a little more in a little later. And then all of the off-axis measurements, which included the above, plus certain things that we could do off-axis, such as vignetting, ghost images, and not even shown on this chart, but we also include making measurements of the background to the detectors that were inside the chamber. And we also looked for fluorescence X-rays that could come from parts of the mirror or the mirror assembly. So to define the subphases of the Herma calibration, and this was important because we prioritized the tests we were going to do in terms of the subphase. So there was a subphase A in which we surveyed all the properties of the Herma. we have a specific objective to reveal all possible surprises. You know, maybe one of the shells was grossly misaligned, maybe something was occluded and gave a grossly different area. Of course, that didn't happen. And we had subphase B, where we actually performed the minimum required calibrations. And the objectives of this phase were that we could fly a 1% calibrated Herma if the properties were substantially as expected. So we planned the measurements that would be needed. We didn't plan measurements that might have been needed if there were some irregularities in the Herma that we hadn't anticipated, and if different measurements had to be made. So that would have been subphase C, guided by the results of A and B, to provide necessary additional measurements that were needed, and then to the extent we could to over-determine parameters and validate the level of the calibration precision that we had made. So we for calibration, we prepared a very large book of calibration plans, and we characterized all the different measurements that we were going to make at different energies with the different calibration phases, A and B. We can see off-axis measurements are all category B. Most of the other sources other than aluminum, carbon, iron are category B measurements. And there's something called wing scans that I'll talk about in a minute. The ENDS survey, this is what I mentioned before about tilting the mirrors so that we could get some information about the exact incident grazing angle and at the error of the area, covering the area of the ends. Because I didn't explain, but at the divergent angle, you don't actually reflect rays off of the entire mirror. I mean, that's why a mirror vignettes, because you don't get to use the full area of it when you're off axis. So essentially, even what we called the on-axis measurements were slightly off axis because of the divergence of the beam. Okay, so then as part of this presentation, actually I'm jumping back in time now to the a presentation a couple of years before doing the calibration to show that what we would do to process and analyze the data at in the SAO mission support team and in conjunction with the AXAF Science Center. So we defined a layer approach where level one was validation of calibration operations. We validated that we could do the operations. Level two would validate the data. I'm sorry, level one validates the data. Level two is doing the data reduction offline, and level three is the detailed analysis and producing the final performance parameters. Okay, my verbal slips there showed that I learned to do Fortran where integers started at 1 and I never learned C where they start at 0. Okay, so for level 0 of the data acquisition, this was part of the deliverable software that actually operated the calibration equipment. It examined an individual calibration operation to assure that it completed successfully. For example, that all the proportional counter spectra showed a line within the range that was expected. in this presentation, we emphasized the fact that we needed to define completion criteria for these tests and a decision tree for failed operations, which we did by and large in the interim till calibration started. Okay, then for level 1, calibration data validation, this grouped according to given test sequences and performed simple data manipulations with the objective of showing that we're getting enough counts that that we have statistics that are adequate and so on. A rough comparison to the performance prediction model, and at this level we produced hard copy plots, for example, of spectra of counting rates. This verified that calibration data of sufficient quality had been obtained. So then we could move to the offline analysis, which during the AXAF calibration, there was the second floor where the actual calibration operations were taking place. And then there was the third floor, largely staffed by the AXAF Science Center that was doing the analysis. So then on that third floor, the data reduction took place where they extracted spectral fits, made dead time corrections, and so on, looked at images from the ring focus tests. And we scoped the amount of work needed for that as something like 10 labor years total. Then there was the final data analysis to produce the final calibration information that went to the AXAF Science Center and ultimately to the users. And so these would do things like correcting for mechanical distortions, analyzing the wing scan data for micro roughness of the mirrors to put into the mirror model, dust contamination, measurements of encircled energy, corrected for the ground calibration effects, and so on. So consideration of the discrete ground calibration effects was certainly an important part of planning and carrying out calibration. And certainly the relevant elements that would differ from the on-orbit conditions, first and foremost, gravity. The mirrors are heavy and they would sag. They were offloaded, but of course not perfectly to a zero G environment. So the combination of gravity and the mechanical offloaders needed to be considered. A thermal environment, the finite source distance and size, obviously, the amount of contamination, the fact that we determined focus differently on the ground than on orbit. On the ground, we determined focus by measuring the centroid in different quadrants of the mirror. When the mirror is in focus, then those centroids all have to come to the same position at the focal plane. On orbit, we couldn't shutter the mirror or look at any small fraction of the mirror. We had to look at the mirror as a whole, and we just scanned through a focus position and determined the best focus by the most concentrated image that we measured. Fortunately, the depth of focus is relatively large for AXAF. It was about 100 microns, and so that was a reasonable thing to do on orbit. Material instabilities. When you get up on orbit, you start having outgassing, particularly from aluminum, which absorbs water a lot. You have epoxy creep to consider. So those were all things that needed to be considered in correcting ground calibration measurements to on orbit. on orbit, also, we dither the telescope over many pixels on the sky, whereas we kept it rigid on the ground. So the wing scans were used for two important purposes: to assess the surface roughness scattering of the mirror and to assess the amount of particulate contamination. So here's the key equation for wing scan and large angle scattering. The surface brightness that you measure depends on the intrinsic roughness of the mirror as a function of spatial frequency along the mirror, and it depends as the energy to the fourth power, inversely as the wavelength of the photons to the fourth power. So it's a very strong dependence. Scattering from micro roughness is predominantly in plane. It makes a streak like this in your measurement. The scattering from particles is a diffraction process. It's sort of quasi-isotropic and makes a round image due to particulates. So particulate scattering, you're particularly sensitive to at the lowest energy. So we measured at the very lowest energy, the carbon K, and we compared to these predictions for different levels of particulates. So here's the surface brightness. It's over about 6 orders of magnitude. So for 10 to the minus 6, 10 to the minus 5, 10 to the minus 4 fractional surface area covered by particulates, we have these predictions of what the surface brightness would be. And the requirement was actually to have about no more than 10 to the minus 5 coverage, because the particle surface coverage has an amplification factor of about 1,000 in going from its effect from just the normal surface area covered to the surface area that's occluded due to the fact that you've got a grazing angle that's approximately 0.01 radians, so which magnifies by about 100. Plus you have shadowing either before or after the particle. You have 2 mirrors on which particles could accumulate, and you have the approximate geometric occlusion and diffractive cross section that are equal. That gives another factor of 2. So that defined the requirement for particulate scattering. So you see that we measured as we went off axis, we measured with increasingly larger apertures. Remember, the scale is 3 millimeters is 1 arc minute at the focal plane scale of the Herma. Then we use a ring focus measurement to help us diagnose or to verify the effects of gravity. So ring focus is an interesting phenomena. On orbit, for a source at infinity, you would focus down here. At the finite source distance, your focus, is 1 over the source distance and then 1 over the mirror focal length to derive the offset to the finite distance focal plane. So the offset is actually about 190 millimeters, a fairly large amount for this for the mirror. But intermediate to that finite distance focal plane, which also isn't a perfect focus either, these rays all cross in principle at an exact at an exact offset distance. They're not in focus, of course, but because they're making rings. So we made with the high-speed imager, we made the image of the rings. This image is made with iron K. You can tell because the outermost ring has a very low reflectivity. And we can see the bulges in the widths of the ring focus as a function around the ring due to the gravity sag and the effect of the offloaders. So just as an example, again, this was from the Vita. Here's measured data of what the full width half maximum was. And this data was analyzed and ground effects were deconvolved using Lucy deconvolution to deduce that we had a full width half max that was actually only 0.19 arc seconds, even though we measured something that was like 0.4 arc seconds in the raw data. The requirement was to measure less than 1/2 arc second in the raw data in order to, of the verification engineering test article, in order to gate the approval of the AXAF mission. And we did make that measurement by a certain specified date. The mission nonetheless was canceled subsequently and as we know, reconstituted. So then as part of our book on planning the calibration observations, we pictorially mapped out what we were going to do. So for example, here we showed where all the aluminum off-axis measurements were going to be made. Here we showed it what different energies we would make off-axis measurements at different off-axis angles. This shows the pinhole scans. And again, 100 microns is 2 arc seconds scale. So very near the core, we used very small pinholes, 5 or 10 micron size pinholes to greatly oversample the expected point response function. And then we needed to use gradually larger pinholes as we went further and further away, just in order to get statistics. Because of course the surface brightness of the point response function drops off very quickly. And then similarly to show the wings scan pattern. We prepared single test summaries for all the tests we planned to do, and then filled them in with the data of the tests. So here's a particular test for a point spread function with aluminum. Here we go, aluminum. We had an aluminum source target, an aluminum filter. This is the voltage and current that produced the kind of X-ray source flux that we wanted. We got our focal plane counting rates that we expected. And this test consisted of moving to 6 different positions with 100 seconds exposure at each position, a total time for the test then 600 seconds. So all of this is in a very, very thick book that was the performance predictions for the first phase of the Herma calibration, prepared primarily by the AXAF Science Center. And that is about the end of the hour, and I'll conclude what I'm going to say, and I could just simply repeat that the model is the calibration. Thank you.
All right, thank you, Dan. Did anyone have any questions or comments they'd like to ask now? Okay, not seeing any hands or anything in the chat. So I guess with that, we would just thank you for that great talk, Dan.
Okay, you're welcome, and good luck.
Thank you. We'll see you all next week.
All right, thank you,
Thank
Dan.
you very much.
Thanks for that wealth of information.
Thank you, Dan. That was amazing.
Thank you.
Thank you, Dan.
Well, thank you all.